In the shallow water near our coast, a tsunami is a mountain of energy that turns a city into matchsticks. But if you're in a ship in the middle of the deep ocean, you might not even realize a tsunami has passed beneath you. This isn't luck, it's physics. Why does the ocean's deadliest wave become invisible to a ship just miles away? And why does that same wave transform into a death trap the moment it hits the continental shelf? Today, we are going to perform a physics autopsy on the relationship between massive cargo ships and the most destructive wave on the planet. To understand why a ship survives, we first have to stop thinking about tsunamis as waves. Most of what we see on the ocean is wind-driven. Wind perturbs the surface layer, creating short wavelengths that break and crash. But a tsunami is born from a different mechanism. When an earthquake jolts the seafloor upward or downward, it displaces an enormous volume of water instantly. That displacement becomes a pulse moving through the entire water column, from the seabed all the way to the surface. This is the critical distinction. A wind wave's a surface ripple, a tsunami's a bulk rearrangement of the ocean itself. Because the disturbance is so large, the resulting pulse has wavelengths that are staggering. Typical tsunami wavelengths range from 100 to 300 kilometers. A commercial jet cruising at 800 kilometers per hour would need roughly 15 minutes to fly across a single wavelength. The pulse moves at roughly that same speed. Because the wavelength is so long, the period is extreme. A single wave crest can take 20 to 30 minutes to pass a fixed point. The ship has half an hour to rise to the crest and another half hour to descend into the trough. The motion is slower than most ordinary tides, and that's where most people picture it wrong. They imagine a giant wall of water racing across the ocean. That image is completely backwards. Compare that to the ship. An ultra-large container ship stretches about 400 meters from bow to stern. That sounds enormous until you set it against 200 kilometers of water displacement. The hull spans less than 1/500th of the wavelength. The ship's too small to register the slope. It rises and falls so gradually that the crew feels nothing more than a slow change in tide level over 20 to 30 minutes. The deep ocean amplitude confirms this. Out at sea, a tsunami might raise the surface by less than a meter, often just a few dozen centimeters, spread across tens of kilometers of gentle slope. Nothing breaks over, no towering wall forms. There's only a barely perceptible expansion and contraction of the water column passing underneath at jetliner speed, undetectable without precision instruments. Japanese fishermen understood this centuries ago. They named the tsunami the harbor wave. When they were out at sea, the water looked calm. They returned ashore to find their villages obliterated. The wave never disappeared at sea. It remained invisible to human perception. But the ocean is not uniformly deep. That's where the physics autopsy gets interesting. Every continent is ringed by a shelf where the seabed rises gradually from roughly 4,000 meters down to about 200 meters over many kilometers. This isn't just a geographic feature. It's the engineering failure point where the tsunami transforms from a harmless pulse into a lethal wall. The mechanism is called shoaling. As the pulse approaches the shelf, the front of the wave begins to drag against the rising seafloor. Friction slows it down. But the rear of the wave is still traveling at deep ocean velocity, 800 kilometers per hour or more. The entire wave train compresses horizontally, like a spring being squeezed from both ends while its vertical height is forced upward. Here's the key. Energy doesn't simply disappear. The same mechanical energy that traveled harmlessly across a 200-kilometer water column thousands of meters deep is now forced into a column 200 meters tall. With nowhere to go, the energy pushes upward. The amplitude that measured sub-meter at sea grows to 5, 10, or even 40 meters near the coast. The gentle slope the ship rode imperceptibly for 20 minutes becomes a near-vertical wall of water that strikes in seconds. This compression changes everything about how the wave behaves. In deep water, the pressure load on a ship's hull is nearly uniform and changes slowly. In shallow water, the pressure gradient becomes extreme and shifts rapidly. The ship goes from floating on a gentle incline to being slammed by a hydraulic ram that exerts uneven force across its hull. Far from shore, the ship rode an imperceptible swell over tens of minutes with no structural stress. Near the coast, it faces a completely different physics problem. The tsunami is no longer a slow tide. It's a high-velocity current with violent turbulent forces that can overwhelm a ship's propulsion, smash it against breakwaters, or drive it inland with enough force to clear city blocks and snap mooring lines designed for ordinary storms. The 2011 Tohoku event proved this distinction with forensic clarity. Ships anchored in deep offshore waters rode through the event with minimal disturbance, without the crew detecting the pulse beneath them. But vessels in harbors and marinas were destroyed by the compressed energy, not by a simple wave crashing over them. The chaotic currents and collisions in shallow water did the structural damage coastal observers witnessed. The physics are clear, but the real-world response is where most mariners make a lethal mistake. What you do next depends entirely on where you are when the warning hits. The answer's counterintuitive and worth remembering. If you're in deep water when a tsunami warning sounds, the safest move is to stay there. Do not run for harbor. Seeking shelter on land is the wrong mechanical response. The International Tsunami Information Center advises that vessels in depths greater than about 180 meters are generally safe. The danger zone is the continental shelf and nearshore. In 2011, the captain who survived did so by steering his boat into deeper water, away from the coast. The harbors where physics turns lethal. In the deep ocean, a ship is not fighting a tsunami. It is riding an imperceptible expansion of the water column that passes beneath it at jetliner speed, often with no crew member ever noticing. The coast is what transforms physics into catastrophe. The same energy proved harmless when spread across hundreds of kilometers and thousands of meters of depth. But the continental shelf compresses it into a fraction of that space, and that makes it lethal. Ships survive because the energy is distributed. Coasts collapse because that energy is compressed. That is the core finding of this autopsy. If you want to understand the limits of massive machines against the force of nature, hit subscribe. We have autopsied the physics behind the ocean's deadliest wave. Tell us what machine or natural force we should tear apart next. We will see you in the next breakdown.